This is the last video of my algebra presentations using Maxima, and it turns out to be about compound interest. This is something that applies to economics, finance, engineering economics, and so on, but it was included in this textbook for algebra, and so we're going to discuss it right here. And we start by giving you the fundamental formula. Here you have a capital C, certain amount of money that you loaned at an interest of a rate of R per unit per year during T años. It should be T years. Sometimes it's written bilingually. T years. So $1 earns R dollars in a year. So after a year, you have accumulated C times 1 plus R dollars at the actual interest rate. In 2 years, you have C times 1 plus R squared, and so on. So in T years, you will have accumulated a capital equal to C times 1 plus R raised to the T. That's the general formula of compound interest. The capital that you have accumulated with an initial capital lowercase c at a rate of R, interest rate R, for 7 years, for T years, sorry, actually. This could be a different period. You could do monthly, and it could be the number of periods T. And so you can obtain out of that, for example, what is the initial capital, if you know the final capital, the number of years, and the interest rate. And then there's another application of logarithm here. If you want to find the time required to accumulate a certain capital, given an initial capital and a rate R, then you do need logarithms. And if you want the yearly interest rate, you can take logarithm also, and the R is right there, and then you do exponential, since we're using natural log here. And so it turns out that the ratio is equal to the exponential of log C minus log C lowercase c over T minus 1. And so that's why we talk about compound interest. First, because it's useful, and second, because it has to do with logarithms. And so clearing all the values right here, if I give you a capital of $5,800 at a rate of 5%, 5 over 100, in 7 years, and a yearly interest rate, the total capital accumulated will be $8,161.18 after 7 years. And that's the magic of compound interest. You let your money work, it grows. Example 2. What will be the value of a loan capital when initial value of $918.54 in 1 year if the interest is applied every trimester? So if you apply in 1 year every trimester, you have 4 periods. The T will going to be equal to 4. The original capital is $918.54. And the rate, this is the annual rate, 5%, but you divide it by 4 periods. So the actual rate is equal to 0.0125. And so in a year, if you compound every trimester, $918.54 will be $965.33 at an interest rate of 5%. A certain capital loan at interest of 3.5% yearly in 9 years has become $2,254. What was the original investment? So you take your R over 100, 9 years, and the final capital. Turns out that you invested $2,388 at 5%. Example 4. How many years will it take? I lost that here. For a capital of 184 to grow to 1,323 with an 8% interest rate. So we use that. Oh, I should have gone through this one first. Sorry. That is T is equal to 6 years. Example 4, a capital of $700 loan and the compound interest during 5 years will become $851.65. What is the annual interest rate? So clear all the values, assign the initial capital, the time, final capital, and the ratio. It turns out to be 0.0399, so it's rounded out to 4%. Amortization. This is when you have to pay a a annual interest. So the first year you pay A, the second year you pay 8, 1 plus R, and so on. So that at the end of T years, this sum will be equal to the growth of the capital. This is a geometric progression, and so there's another reason why we do compound interest, because it talks about geometric progressions. So if we hold the first term A and the n term AN, will give you these results, and the sum, we remember, is equal to this. And so if we equate that result with the initial capital, then we have a formula for the annuities. Initial capital multiplied by the rate, multiplied by R rate plus 1 to the number of years, divided by R plus 1 to the number of years, minus 1. For example, a city borrowed 500,000 at 4% annual to amortize in 15 years. What annuity must be paid? Load the values in there and calculate that annuity. It turns out that they need to put out $44,970 every year to amortize their loan. Similarly, if you're building a capital, in this case the formula is slightly different, because you put your investment, your first contribution. In 1 year you have contribution plus 1 plus R, and second year this, and so these all add together to the capital that you want to build. In the right hand side we have a summation of a geometric series with this initial value and this nth value after T years, and so the sum of all those terms is going to be equal to these. They should be equal to the capital you want to build, and so the formula to use is this one. If you want to build a capital of C, your yearly contribution should be equal to C times R divided by R plus 1, parentheses R plus 1 to the T minus 1. Clearing everything here, we're going to do a simple example. What contribution I at the rate of 5% annually will produce after 20 years? A capital of $80,000. So you need to contribute $2,304 dollars every year to build $80,000. And so those are some of the very simple applications of compound interest. And the main reason why they show up in this video is because of the fact that we use logarithms and geometric progressions. And with these, we're going to end up this series of videos about algebra applications in Maxima.